Gamma ray bursts are flashes of gamma rays that are emitted from high-energy explosions. There is no brighter electromagnetic event in the universe, lasting from milliseconds to a few minutes. They shine brighter than a supernova and 1,000,000 trillion times more than the sun. On the electromagnetic spectrum, gamma rays are in the same family as X-rays, radio waves, and light. Gamma rays are much shorter in wavelength than visible light and carry a lot more energy, that equivalent to a nuclear bomb explosion. Since the Earth's atmosphere blocks gamma rays, they went undetected until astronomers put gamma ray detecting telescopes in space. They discovered the bright bursts of gamma rays originating far from the solar system. Their sources are billions of light years away. Astronomers found two types of bursts, short duration and long duration. Both types were created by different means, but the end product is always a black hole. Later, ultra-long bursts were discovered. These arose from the death of a supergiant star. Gamma ray bursts can be emitted from two neutron stars colliding. The colliding neutron stars produce an ultra-strong magnetic field structured like the jets needed for a gamma ray burst. After merging, it then transforms into a rapidly spinning black hole. Though the collapsing star model is the most likely source of gamma rays, there are also some short-duration bursts that occur with no star formation and no massive stars present, such as elliptical galaxies, and usually with a redshift z of 0.225. A cosmological redshift is the observed spectral lines shifted to longer, redder wavelengths. Caused solely by the expansion of the universe, the value of the cosmological redshift indicates the recession velocity of the object or its distance. A galactic halo is a nearly spherical volume of thinly scattered stars, globular clusters of stars, and tenuous gas observed surrounding spiral galaxies. While some gamma ray bursts seem to radiate from them, they are not found in the galaxy halo. Another way that gamma ray bursts can be produced is by the death of a large star. The repulsive electrical forces between the atom's nuclei overcomes the gravitational forces, causing a massive, bright, short-lived explosion called a supernova. As a star grows older, the strength of stellar wind determines how much of the hydrogen atmosphere is retained. The star's envelope of hydrogen would take a long time to complete its fall into the black hole. This provides a long-lived fuel source to power an ultra-long gamma-ray burst jet. One supernova lighted the Earth's sky in 1054, becoming so bright that for a few weeks it was visible in broad daylight. Today, almost 1,000 years later, the remnant of that supernova is visible through a small telescope as the Crab Nebula. The Crab Nebula is studied well in an interesting piece in the universe. It spans about 10 light years. In the nebula's core lies a pulsar, a neutron star as massive as the sun but small-sized. The Crab pulsar rotates about 30 times per second. Dying massive stars that are surrounded by a thick shell of gas can explode even more violently than hypernovae. The mass must be high enough for the star to undergo an energy crisis, with its core running out of fuel and collapsing under its own weight to form a black hole. The core of a massive, low metallicity, rapidly rotating star collapses into a black hole. According to the hypernova model, the explosion in the spinning black hole would continue to produce great jets of energy that energize the leftover material surrounding it. The core of the star collapses to be a supercompressed spinning black hole, which stirs and energizes the wreckage around it to briefly emit a tremendous burst of gamma rays. The burst area also continues to glow with other various electromagnetic waves. From the black hole, thermal radiation is released as gamma rays emitted by high-temperature plasma. As they reach the interstellar medium, they decelerate rapidly, emitting optical light and X-rays. The afterglow is detectable by satellites. The Earth's atmosphere does a good job absorbing gamma rays. The short effect of gamma ray absorption would be an increase in ultraviolet radiation. It could reach potentially dangerous levels, but it would not have a significant impact on life on Earth. The long-term effects from a nearby burst are more dangerous. Gamma rays cause chemical reactions in the atmosphere that create nitrogen oxide and gases. They deplete the ozone to the extent that it is enough to cause a dangerously elevated UV index at the surface. Nitrogen oxides can also cause photochemical smog, which darkens the sky and blocks out parts of the sunlight spectrum. This would affect photosynthesis on a microscale. The smog could cause the Earth's climate to cool, producing a cosmic winter. The elevated nitrogen levels in the atmosphere could produce nitric acid rain. This substance is toxic to a variety of organisms, but it cannot reach levels that would cause a serious global effect. A gamma ray burst will mostly damage life by raising the UV.